world as solids, made of atoms. Today I'm going to show you that the universe is actually made of phantoms who disappear when you try to trace them. Hello, honorable judges. I'm Arya Munglani from DPS Udayp, class 11th, and I will be giving a sort of seminar about the world of quantum physics, purely by intuition, no boring calculations. Okay. So what is quantum physics? Quantum, what is quantum physics? Quantum physics is a branch of physics science that studies the behavior of matter and energy at the smaller scales, atoms, photons, electrons, and other subatomic particles. Unlike the predictable world of classical physics, quantum physics operates by fundamentally different rules. At the quantum level, the certainty promised by our everyday world is taken over by probabilities. Particles are not just tiny lumps of matter, they exhibit dual nature. They are both discrete packets of energy and also act as waves of probability. It is everywhere and nowhere at once. So we move on to the double slit experiment. When we fire an electron at two slits, it doesn't choose one. It behaves like a wave interfering with itself. This is the double slit experiment. When no detector monitors which slit the particle passes through, it behaves like a wave, going through both slits simultaneously. But creating an interference pattern, of course, on the screen. And when we try to trace the path it takes, the whole pattern disappears. And well, how do we try to detect it? That's where we come to quantum eraser. Right? If you try to detect the path a photon took, the wave or interference pattern, it vanishes. Right? The quantum eraser experiment was first performed in 1999. It used entangled twin photons. Okay, one photon was the signal photon and the idler photon, which took the longer path than the signal photon. And if you take away the which way info from the idler, and then we somehow gain the interference pattern again. Uh, and if we ask the question, why did it in the first place? The quantum system to act as if it is multiple states at the same time until it in which a quantum system can exist in multiple states or configurations simultaneously. For example, in computing, we use bits, which can be in two states, one or zero. But a qubit is a quantum system which can be in two states simultaneously, zeros and one simultaneously. Now let's talk about the Heisenberg theory. Werner Heisenberg, a trace scientist, discovered a fundamental limit. At a given moment in time, it is impossible to measure both momentum and position of an electron simultaneously. Why is this? Well, let's see. The electron speed in the first orbit of a hydrogen atom is approximately 2.2 multiplied to 10 to the power 6 meters per second. That is too much, and it is impossible to measure such momentum or position without. We can better understand this by an example. So this, by a tennis ball analogy, you can see this is a sharp shot of a tennis ball. You can measure its position. You can see its position clearly, right? But if you see here, it's a blurry shot, and you can see its momentum where it's going. You can calculate the momentum by measuring the distance between them, but you cannot see its position. Where is it? Here, or here? Quantum tunneling. Imagine a particle and an energy barrier in the shape of a hill. Okay, classical physics says that in order for the particle to go past that barrier, it would need to have enough energy to go up and over the hill. In quantum mechanics, there is a non-zero probability it can appear on the other side, even without sufficient energy. The particle leaks or tunnels through the barrier, emerging on the other side. We can see practical proofs. In real life, quantum tunneling is integral to our existence and technology. in solar fusion, hydrogen atoms are fused to form helium atoms, releasing energy into light, which makes our sun shine. Okay, so one step in this includes the bonding of two protons. Right, the protons need to come so close that they bond together and form a nuclear bond. Right, but classical physics says that because they're like atoms, they will repel each other, and it is near impossible. But it happens. It is rare, one in a trillion, but it still happens. Why? Because of quantum tunneling. Your mobile phones have flash drives, right? Flash drives work through quantum tunneling. Electrons quantum tunnel through the insulated layers and process the data that way. Thank you.
I am Zorakada, a student at Delhi Public School level, studying in class level. In this PPT, today we discuss about quantum physics. These content will be provided in this PPT. What is quantum physics? Quantum physics is the behavior of matter and energy at atomic and subatomic level. At this stage, the rules of classical physics does not apply. It also explains that why electrons do not collapse into the nucleus and why semiconductor works. These are the scopes of quantum physics. First is quantum mechanics. It happens with particle behavior. And second is quantum field theory. Particle as field existence. Third is quantum information science, storing and processing info. Fourth, quantum computing, qubits and superposition. Technologies like MRI, lasers, quantum computers, and semiconductors rely on this principle. Now, we will talk about quantum mechanics. Quantum mechanics is a foundation of the quantum physics. It uses wave functions and probability to describe particle behavior instead of fixed trajectories. Now, these are some principles of quantum mechanics. Quantization of energy. Particles can only have discrete energy levels. Wave particle duality. Particles exhibit both wave and particle characteristics. Superposition. Systems can exist in multiple states at once. Uncertainty principle. Exact position and momentum cannot be measured simultaneously. It also explains the spectral lines of hydrogen atom, photoelectric effect, and atom behavior. Now, quantum states and superposition. A quantum system can exist in multiple possible states at the same time. The final state is determined when the measurement is performed, collapsing the system into one outcome. Qubits in a quantum computer exist in superposition, allowing parallel computation. Now, quantum measurement. In what is quantum measurement? In quantum physics, measurement affects the system. Observing a particle can alter its state, which is a fundamental property of quantum systems. Measurements of qubits in quantum computing determines final output. Now, next is quantum entanglement. Entanglement occurs when two particles become correlated so that the state of one instantly affects the other regardless of the distance. Example, it used in secure quantum communication, quantum key distribution, and quantum teleportation experiments. Now, quantum field theory. Quantum field theory combines quantum mechanics and special relativity. It treats particles as existence in underlying fields and provides the theoretical basis for modern particle physics. It also predicts particle behavior in CERN experiment and explain creation of particles. Now next is quantum electrodynamics. Quantum electrodynamics or QED describes the interaction of charged particle with electromagnetic field using quantum principles. It is extremely accurate in predicting phenomena like scattering of electrons and photons. The design of lasers, particle detectors, and understanding electron, photon. Next is quantum chromodynamics (QCD). Quantum chromodynamics or QCD explains the strong nuclear force that binds quarks together inside protons and neutrons. It describes the structure and interaction of fundamental particles inside the atomic nuclei. Understanding particle collisions in acceleration and nuclear reaction. Quantum information science. Quantum information science studies how information is stored, processed, or transmitted using quantum systems. It combines physics, maths, and computer science, quantum computers, quantum memory devices, and secure quantum networks. Next up is quantum computing. Quantum computing uses qubits, which can be in superposition, and time element and superposition allow quantum computers to solve complex problems exponentially faster than classical computers. Simulating molecule for drug discovery, solving factoring problems, and optimization of algorithms. Quantum cryptography. Cryptography ensures secure communication by using quantum states. Any attempt to eavesdrop disturbs the system, making intrusion detectable. Application. Quantum key distribution or QKD is used for high secure data transmission.
कोड नंबर 220। कृपया करके सभी समय का ध्यान रखिए। हम समय सीमा में बंधे हुए हैं।
Good morning, respected judges and my fellow participants. Myself, Rudraksh Kumawat from Delhi Public School. Today, I am here to talk about one of the most fascinating and counterintuitive ideas in quantum mechanics, that is, quantum tunneling. In our everyday life, objects follow a very common rule. For example, a ball cannot cross a wall until and unless it has enough energy. However, at the atomic scale, nature behaves very differently. Quantum tunneling shows us that the microscopic world does not follow our everyday intuition. Now, what is quantum tunneling? Quantum tunneling is a phenomena where particle crosses a barrier. Even when it does not have enough energy to do it, right? You can see the particle is crossing the barrier even when it does not have enough energy. According to classical physics, this should be impossible. But in quantum mechanics, particles like electron do not behave like a point object, they behave like waves. Because of this wave-like nature, there is a small but real probability that a particle can appear on the other side of the barrier. This process is called quantum tunneling. Now, what is the difference between classical and quantum physics? To understand this better, in classical physics, if we roll the ball, if it has enough energy, it will cross the hill, but if it doesn't, it will roll back towards us. Now, in quantum physics, if you roll the ball and it does not have enough energy, it will not just stop at the starting of the hill. It will, some of the waves of the ball can cross the hill and appear on the other side. Now, the wave nature of particles. In quantum mechanics, particles such as electrons are described by something called wave function. This wave function does not tell us the exact position of the particle, but instead it tells us the probability of finding the particle at the particular place. Before the wave function is spread out, it does not suddenly stop at the barrier. A small part of it, energy barrier and tunneling mechanism. An energy barrier is a region that a particle cannot cross until and unless it has enough energy. In quantum tunneling, the wave function of the particle penetrates into the barrier gradually decreases instead of stopping suddenly. If the barrier is thin enough, the wave can emerge on the other side, as you can see right there. The higher or wider the barrier, the smaller the probability of tunneling. Now, the uncertainty principle. Quantum tunneling is also connected to Heisenberg's uncertainty principle. This principle states that certain physical quantities such as energy and time cannot be measured exactly at the same time. quantum tunneling in the sun. And
Good morning, everyone. Good afternoon, everyone. My name is everyone over here. My myself, I am from DBS Udaipur and NTA aspirant, and I'm honored and I'm grateful that I have chance to say something about Schrodinger equation in this seminar. Well, when we talk about this equation, the one of the most important thing is that it is known as the foundation of quantum mechanics. Why? It's because of a very special thing. In one of the articles which I've read about this, it was written that Schrodinger was known as the Shakespeare of quantum physics. And you know why? Because like Shakespeare, today's many of the Indian drama and US drama, they still use Shakespeare's drama, Shakespeare's ideologies and everything. Similarly, in today's world with quantum physics, physicists still use this equation. Now, first to understand this equation, we need to understand what is quantum mechanics, what is quantum physics, why is quantum physics, and how quantum world is different from the regular world. Well, what we see right now is a car moving with a simple acceleration, a car moving with a simple force, applying a simple force, applying a simple force. It's wrong. But the thing over here is, which is quite not normal, is that this thing applies on a large scale, on a large object, but it does not apply on a single point-size object, like an atom or anything, right? Or a molecule. For that, some of the physicists believe that we need to discover something which can, help us to find a way to identify everything like this, like where it's of this energy levels and everything. So they discovered quantum physics. It is basically for atomic and subatomic studies of an atom, right? So this man over here is Sir Erwin Schrödinger. He was born in 1887. I was just giving you a brief idea and history about this man. He was born in 1887, Austria, and he got his what do you call it? Um, Nobel Prize in Physics in 1933 because of his invention and his discoveries, his theories. And he was known for his contribution, like he treated particles like wave instead of point function, which was revolutionary because at that time, Newton, Heisenberg, most of the like scientists believe that because Newton was pretty old at that time, 1644, and I'm talking about 1933. At that time, scientists do believe that, physicists do believe that an atom is a point size, but over here we can see that atom is a wave structure. He revolutionized our ideology. Now, mathematical form is pretty simple to identify this equation. It's I half blank delta psi upon delta t is equals to minus. It's a normal equation, right? It's an equation given by minus. So mathematical representation of idea is revolutionary idea. Now, need for Schrodinger equation is simple. It's Newton laws that describe the motion of objects. Maxwell equations that describe electromagnetism. But these are not applicable for atomic scale. For atomic scale, Schrodinger needed something to understand it, and he gave his entire life to this thing. So he given this equation, Schrodinger equation, which was about that it will give us information regarding the movement of the atom, where it's moving, the amount of energy it can hold, and etc. etc. Please. Now wave function, it physically does not have any meaning. Its modulus square does have meaning. It just shows the yeah, probability density, that where probably an atom can go. It cannot really give us the exact location of it, but it can give us a probability or a rough idea that where it can go. Now, probability interpretation is again what I said, quantum mechanics probability is a question of electron connect So it's the good part over here is that Heisenberg's uncertainty idea, which I really wanted to mention over here, is more certainty in position, less certainty in momentum. Right? Now, particle in a box application is simple quantum model, particle trapped in a one-dimensional box, allowed energy values that discrete energy cannot be continuous, result energy levels are quantized. Simple. Now, importance of Schrodinger equations, it explains atomic spectrum. It is important for quantum computing. It is important for foundation of quantum chemistry, by the way. Now, limitations were simple, does not include relativity, and fails at speed close to the speed of light, right? It was not able to, it cannot describe particle with spin accurately. So through the Schrodinger equation changed our understanding of nature, replaced certainty, probability, and essential for modern physics and technology. That's just like 0.1% of his entire achievements. The most important thing which I studied over here and which I thought that I should point out is that he was a revolutionary before a scientist. Because he revolutionized the way of thinking of people. Because you people used to think that atom is just a point-sized object, but he believed that it was a wave. So he just revolutionized every single thing. That's what I believe. Thank you so much.
Number 222.
Good morning, everyone. Myself Arup Kandharia, and I'm representing my school, DPS, Delhi Public School, Udaip. Today, I would really like to talk about a very strange yet a very powerful and very interesting topic, which is quantum entanglement. Now, before we jump into quantum entanglement, let us just know what is quantum physics. Quantum physics is very much different from our everyday physics that we learn in our school. These quantum physics is the physics which deals with the study of the building blocks of our nature, which are electrons, photons. These are completely different from as they follow very different rule set and make very different things. Now, what is quantum entanglement? Quantum entanglement is a phenomenon, is a state when two particles get connected to each other in such a way that they cannot be separated regardless of what they become. This means measuring one particle immediately gives the information about the other. So, to understand quantum entanglement, let us take two coins in which we know the result that if one side shows heads, then the other will show tails. So if one information is supplied to one particle, then the other will immediately transmit it. So why is it strange? Is it strange because the information is not basically just traveling; it's automatically indicating the other particle to show something. It's faster than light, breaking classical rules, and distance is irrelevant. Now we can talk about some practical applications of quantum entanglement that are quantum computing, quantum tunneling, quantum teleportation, quantum cryptography, and quantum sensing. So, what basically is quantum computing? To understand computing, let us know a very small particle like qubit. Qubit are digits that work in the way of quantum physics. So it helps in parallel processing and unpredictable. Now, another application of quantum entanglement is quantum cryptography. So, cryptography is a state in which there is a very secure connection between the information that is traveling. It cannot be detected as little interference can completely change the information. Quantum teleportation. Quantum teleportation is basically the traveling, the automatical transmission of information from one place to another. It's important to clarify that this process does not involve physical objects or people. This only matters on the information. Now, I would like to conclude by saying that it's strange, but it's like very much important in modern world because technology is very much advancing. Modern quantum science will be basically acting upon this quantum entanglement only. Thank you.
Thank you, everyone.